Hello, my name is Rishit. I am a research scholar in the Department of Mathematics at IIT Palakkad. Uh, I'll be lecturing on some basic topics on topological vector spaces. This is the first video on the basic topics on topological vector spaces. In this video, I'll be teaching some I'll be introducing some basic definitions and some basic definitions and some examples. So let us start with the prerequisites. Uh, let us start with some prerequisites. You are expected to know some basic topics like linear algebra, functional analysis, and topology. Okay, so you are expected to know some basic topics on linear algebra, functional analysis, and topology. So let us start with some basic definitions. Before that, the reference book for this is Functional Analysis by Walter Rudin, the reference book. By Walter Rudin. Okay, so some definitions. Let X be a vector space over K. Here we are considering K to be either real, the field of reals, or the field of complex. So X is a vector space either over R or C, and let A comma B be non-empty subsets of X. And let alpha belong to K. So my first definition is I am defining two sets. One is A plus B. A plus B is defined as the sum of all small a plus small b, where A is in capital A and B is in capital B. Similarly, I am defining alpha A as alpha A, where A varies over capital A. Right? Some of these definitions you must have seen already. I am just recalling some of the definitions. Second one, the set A is said to be convex if t times A plus 1 minus t times A is contained in A for all t belonging to closed interval 0, 1. My third definition is the set A is said to be balanced if alpha times A is contained in A for all alpha in K with mod alpha less than or equal to 1. My fourth definition is the following. Let the set A is said to be absorbing if for every x in X there exists an S positive such that X belongs to SA. So my set A set A is said to be absorbing if for every x in X there exists an S positive such that X belongs to SA. Okay, now we come to the main definition. Main definition that of topological vector spaces. Topological vector space. We abbreviate it as TVS. Topological vector spaces is abbreviated as TVS. Okay, so let X be a vector space over K. And let tau be a topology on X. Okay, let tau be a topology on X. Then tau be a topology on X satisfying the following conditions. Satisfying topology on X satisfying the following conditions. What are the conditions? My first condition is singletons are closed. Singleton X is closed for every X in X. Singleton X is a closed subset of X is a closed subset of X. This should be true for every X in X, right? And my second condition is, for a vector space there are two maps which are associated with the vector space, right? That's addition and scalar multiplication. The addition map from X cross X to X and the scalar multiplication map from K cross X to X are continuous. This is the addition map. This is scalar multiplication map. Right, the addition map and scalar multiplication map must be continuous. Right, continuous. I have to specify the topology on X cross X and K cross X. So we are considering K to be the Euclidean space. K is the metric on K is the Euclidean metric. And X cross X comma K cross X is given the product topology, or are given the product topology. Okay, so we are considering X cross X with the product topology, K cross X with the product topology, and if this map plus and the scalar multiplication map are continuous along with singletons being closed, then X with tau is said to be a topological vector space. Then X is said to be a topological vector space. And this topology tau is called as a vector topology. is called as a vector topology. Right? So by a neighborhood of a TVS, okay, let us, before that, let X be a TVS and let X belong to X. Then by a neighborhood of X, we mean an open set, U containing X. Okay. Now let us understand what we mean by addition, continuity of addition and scalar multiplication. What does continuity of this addition map and this scalar multiplication map really mean? Here you have to recall the definition of continuity in a topological space. Please go back and recall the definition of continuity on a topological space. So let X be a TVS and let X comma Y belong to X and let alpha belong to K. Let V be a neighborhood of X plus Y. So V is a open set containing X plus Y. By continuity of plus, there exist neighborhoods V1 and V2 of X and Y respectively, such that, or satisfying V1 plus V2 is contained in V. Right? And what do we mean by continuity of scalar multiplication? So let W be a neighborhood of alpha X. Then there exists R positive and a neighborhood V of X such that for every beta in K with mod beta minus alpha strictly less than R, we get that beta times V is contained in W. So this is the meaning of continuity of scalar addition, continuity of addition, and this is the meaning of continuity of scalar multiplication. Okay. So let us give some examples of topological vector spaces. Examples: every norm linear space is a topological vector space. Every norm linear space is a TVS. Second example, let omega be an open subset of Rn. Rn with usual topology, Euclidean topology. Then consider C of omega. This is a collection of all functions f from omega to R such that f is continuous. then this C of omega is a TVS. Then it can be shown that C of omega is a TVS. I'll be not proving this in the course of these videos. I'll not. It's beyond the scope of these videos to show C of omega is TVS. So, okay, this is just for the sake of having some examples. So, C of omega is a TVS. I'll give some simple exercises that you need to prove. Some exercise. Let X be a TVS over K. Fix X naught in X and lambda naught not equal to 0 in K. Okay. Define Tx naught map from X to X and m lambda naught a map from X to X as Tx naught on X is equals to X naught plus X naught and m lambda naught of X is a map defined as lambda naught times X. Show that Tx naught and m lambda naught are homeomorphisms. Respectively. What do we mean by a homeomorphism? You have to show that Tx naught is a bijection, Tx naught is continuous and Tx naught inverse is also continuous. Similarly, you have to show m lambda naught is a bijection, m lambda naught is continuous and m lambda naught inverse is also continuous. That is the meaning of a homeomorphism. Okay. The second exercise that I want you to show is, let E be a subset of X, then E is open if and only if X plus E is open for every X in X. This is also simple. It actually follows from the first exercise. This property 2, this property is called as translation invariance of tau. Property is called as translation invariance of tau. Translation invariance of tau. Okay, my handwriting is bad. Translation invariance of tau. Okay. So let us recall the definition of a local base. Moving on, recall. Let X be a topological space. Let X comma tau be a topological space. And let X belong to X. A collection B. Okay, how should I put this? Let B sub X be a subset of tau let B sub X be a subset of tau. Then B sub X is said to be a local base at X. a local base at x if for every neighborhood u of x there exists some element b in bx such that b is contained in u. I have to add one more thing here. Let b be a collection of tau such that every member of bx contains x. Every member of b sub x is a neighborhood of x. Okay, let b sub x be a sub collection of tau. What is the property that this b sub x has? The property is that every member of b sub x is a neighborhood of x. Then this collection b sub x is said to be a local base at x if for every neighborhood u of x there exists an element b in b sub x such that b is contained in u. Now in the case of TVS, in the case of topological vector spaces, it is enough to consider local base at 0. Enough to consider local base at 0. Why is this? This is because of this translation invariance property of tau, right? So if we have a topological vector space x comma tau, then instead of considering a local base at any random point, we can consider a local base at 0, because once we have a local base at 0, we will have a local base at every other point of x, right? We can just add that yeah, you understand what I am telling? If b is a local base at 0, then what we do is we consider this b sub x. What do? We consider b x plus b belongs to b, script b. Then this b sub x is a local base at x, right? This we get from this translation invariance of tau, right? Okay. So by convention, in the future videos, by a local base of TVS x, we mean a local base at 0. Okay, so in future videos, whenever we mention the word local base, we mean it is a local base at 0. Okay, now one more exercise. Tau is completely determined by a local base at 0. Tau is okay. Before what is tau? Let x be a TVS and let tau be the vector topology. On x. Then tau is completely determined by a local base. What do I mean by this? So if b is a local base of x, and if G belongs to tau, G is an open set in X, G is an open set in X, then this G is a then G is a union of translates of members of B, some members of B, union of translates of some members of B, some members of B, right? That is, there exists some X alpha in I, X alpha in X. Okay, before there exists an indexing, that is, there exists an indexing set I. How should I put this? That is, G is a union of X alpha plus V alpha, alpha varying over I, where X alpha belongs to X and V alpha belongs to B. Okay, so G is a union of translates of members of B. Okay, now yeah, so coming to an important definition, a topological vector space X is said to be locally convex if there exists a local base B of X such that every member of B is convex, that is, for every V in V, V is a convex subset of X. So a topological vector space is said to be locally convex if there exists a local base B of X such that every member of B is convex. So I'll be stopping here now. We'll continue in the next class.